Welcome to the fourth lesson in Chapter 2. This is Section 2.5 in your text. And last lesson we talked about polynomial functions and solving them. This lesson broadens your scope a little bit. Now we're going to start talking about rational functions. Rational functions are going to have a polynomial in the numerator and a polynomial in the denominator. And you just need to remember that the denominator obviously cannot be 0. Now, you have already played with a lot of these in Chapter 1, and you've already seen these graphs and we've analyzed them, but we are now adding more tools to your tool belt, so to speak, and we are going to break them down a little bit more and give some things other names and determine how to calculate some of these. So the first thing I'd like to talk about is when we're analyzing the graphs, and I would like you to look at this chart. And again, if you lost this chart, I gave it to you in class. You can print it off in Canvas. That's right. So I've divided this into 3 different groups. Ones that have vertical and horizontal asymptotes, ones that have slant or oblique asymptotes, and ones that have a hole. This also has a vertical asymptote, I'm aware, all right, but it also has a hole. So let's talk about some of these, and I first just want to analyze the graphs. Talk about what you can pull off from just looking at the graph itself. All right, so let's start here. The domain would be the x's, and it would be everything except they're at -3 and 3, right? So remember, you can write this several different ways. The set of all x such that x is not equal to 3 or -3. You can do it that way if you want. Vertical asymptotes, we can tell are equal to this. Now you can't just write 3 and -3. I want the line. X equals -3 and x equals 3. Horizontal asymptote, well, you can tell here that it's at 2. An oblique asymptote, I don't have any slant asymptotes or any diagonal asymptotes, basically. Do I have any holes? It doesn't appear that I do. Do I have any x-intercepts? All right, the x-intercept, it's kind of hard to tell right here, but do you see how that's a little darker there in the middle? If it's a little darker there, that indicates that it actually went above that part of the graph. Let me see if I can zoom in here a little bit. So you can see how that actually is a little darker. It actually does cross there at 0, at 1, 0, and at -1, 0. So we have 2 x-intercepts, 1, 0, and at -1, 0. Y-intercepts, it's really, really, really tiny. You cannot tell what that is, right, from looking at the graph. I can tell you that I know it's at 0 to 2/9. Okay, because I know what the function is, and I'm looking down here at the function. If x is 0, I know that I'm going to have -2 over -9, which is 2/9. But that is very hard to tell from the graph. The end behavior, right? We've done this before. As x is approaching -infinity, over here, if it's getting really, really small, this function is approaching that 2, that asymptote. As x approaches positive infinity, it's also approaching that asymptote of 2. All right, let's look at the oblique. Let's look at this graph. The domain, okay, the x is everywhere except at that vertical asymptote there at 1. So it's the set of all x such that x is not equal to 1. Now our vertical asymptote is there at x equals 1. Horizontal asymptote, I don't have any. My oblique asymptote, it's kind of sometimes hard to figure out from the graph, but it looks like it's going on that line. It looks like it intercepted there at 1, and it has a rise of 1, run 1, rise 1, run 1, rise 1, run 1. So it looks like my oblique asymptote would be a slope of 1, and my intercept is 1, y equal mx plus b. You notice you're not going to have oblique and horizontal in the same graph. Okay? Holes, have none. Intercepts, right there at the origin for both of them. Right? It would be both of their intercepts. The end behavior. Let's talk about that. As x is approaching negative infinity, this graph is also approaching negative infinity. As x is approaching positive infinity, the graph is approaching infinity. All right, let's look at the last example I have right here. The domain is everything it would appear except 1, 2, 3, 4, 5. Okay, so the set of all x such that x is not equal to 5. But that means my vertical asymptote is at 5. My horizontal asymptote, it does look like there is one, right? It's above. It looks like it's there at 1. My oblique asymptote, I don't have any. But there is a hole there at -1. I had to draw that in because remember it's not going to show up on your calculator. Okay? Now, you know it's at -1, but you can't tell really what the point is. That's -1 something, and you can't tell. So I'm just going to put a little question mark there because I can't tell what that is. The next one says x-intercepts and y-intercepts. All right, if I look down here, it looks like it crosses right there at 3. So I'm going to say my x-intercept is 3, 0. My y-intercept, I can't tell. All right, from this graph. I mean, it's less than 1, but that's all I know. And again, if I look down here at the equation, if x's are zeros, I know that I'm at 3/5. But I know that it's hard to tell when you're just analyzing the graph. End behavior. As x approaches negative infinity, you're getting really close to that asymptote, so it's approaching 1. As x approaches positive infinity, you are also approaching 1. Now, what I'd like to do is to point out a few things about the functions. Remember, and we've done this before, you can factor the functions. You know that where you have like factors and they reduce, that a hole exists there. And you've also learned in Algebra 2 about some of the asymptotes. And we just touched on this a little bit in Chapter 1, but I would like to review some of these ways to actually analyze the equation. So that's the second half here of our notes. Let's put into words some of the things that we've already done on the first half. When you're analyzing the equations, you know that the domain, you do this automatically now, but that happens everywhere where the except where the denominator is 0. Remember way back up here we said that the bottom polynomial, the denominator polynomial, is b. And so everywhere except where that is 0 is going to be where the function exists, is the domain. And as you noticed from when you were analyzing it, where the domain doesn't exist, there's a vertical asymptote, because that's where the x will exist. Now I need you to notice that a vertical asymptote, and I need you to make note, will never, ever, ever be crossed by the function. They are firm. The horizontal asymptotes can be crossed by part of the function, as can an oblique part. All right? So let's review some of these, and I know you did them in Algebra 2, but let's go back over them a little bit more. So the vertical asymptotes, again, are pretty easy to determine from the graph, and that looks at the denominator. The horizontal asymptotes, you look at the degree of the numerator and the denominator, of the polynomials in the numerator and the denominator. If you have the degrees are going to be, if you have a lower degree on the top and you have a higher degree on the bottom. I always remember that because that's normal for a normal fraction. You would have a lower number on top and a higher one on the bottom. Then you have y equals 0. Some of you may remember Bobo from when you were in Algebra 2. All right, that means that you had a bigger number on the top, or on the bottom. And so that gave you y equals 0. one of the other options was to look at the degree, and if the degrees were the same, if they were the same number, both x squared, both x cubed, etc., then you looked at the coefficients in the front of the equation. Remember when we had the expanded polynomial, they were the a sub n and the b sub n. This was your EATS DC part, okay, where your exponents are the same. Then you're going to divide the coefficients. Now this is the change from last year, because last year you were told that if you have a polynomial and you have a higher exponent on the top, okay, you were told, Botten, B-O-T-N, you were told if you were bigger on top there was no asymptote. Well, you're smarter now and we're changing that. And there is an asymptote, okay, but that means that you have to do long division. So if you are bigger on top with your exponent, with the degree, then that means that you have what's called an oblique or slant asymptote. And you have to long divide. Okay? And normally it's not synthetic, it's long division. When you're doing the long division, you will disregard the remainder. You are only interested in that first part of the quotient, so disregard the remainder. And we'll talk about that when we do one, and I'll show you. And the wholes we've already talked about, but that's when you have a common factor that exists between both the numerator and the denominator. So this was, I'm going to go through and do example 1. This was the center graph here that we did on our chart, and here's the function. I just want to show you how the long division works when we do, because we determined that that was our asymptote, y equals x plus 1, but I'd like you to see that with the long division. So we look at the rational function, and you see that you have a higher degree in the numerator, 2, and a lower degree in the denominator. So that tells you that you're going to need to do long division. Let's review how we do this. So what value do I multiply by x to get x squared? Well, that would be x. And then you distribute that to both of those terms. So I would have x squared minus x. You subtract, you go through and you change the signs. So now I have, when I subtract, that's gone and I just have x. So I have nothing to bring down. But I multiply x times what value to get x, and that's simply a 1. And again, you have to distribute that to both terms. That gives you x minus 1. You subtract, you change the signs, your x's go away, but you have a remainder of 1. You don't care about the remainder of 1. Very often this remainder will be a fraction and you don't care. This is a remainder of 1 over x plus minus 1 here. If I wanted to write that out, the answer would be x plus 1 over x minus 1. Okay? As x approaches a really large number, this is going to go so tiny, it's basically going to go to 0. So we ignore the remainder. We only deal with the quotient. And if you look back at your notes, the asymptote was y equals x plus 1. All right, so when we come back in part 2, we will start solving some rational equations, not just graphing them. Thank you.